Professional Services, and this is Jeff Doyle, also from the same team. I'll put some pressure on him. Some of you guys might be familiar with him just from his TCP/IP routing book that he wrote a little while back. So I'll defer all hard questions to Jeff. I'll explain a little bit how this is going to work. We thought it'd be a little more interesting to have a live demo as well as the slideware, so that you guys aren't all falling asleep on me in the next 20 minutes. So what we got here is just, I don't know, 7 or 8 PCs running the Juniper software. And this presentation I did at Apricot in Seoul, and that was a full day. So I tried to pare down these slides as much as possible given the time frame. And I also tried, because some of the material also came from courses we give on the topic, I tried as much as I could to take out the Juniper specific stuff, because I realize this is NANOG and I'm not here to sell you any routers. So at times, you know, the features or the mechanisms, how they work, may be Juniper specific, the algorithm, let's say, but I think the concepts are pretty generic across the board. One example is like traffic protection. We'll get into that, and I'll talk about the various ways you can do that. And some of it, when we turn it on and show an example, may be Juniper specific, but I think the concept itself, you know, applies to MPLS traffic engineering. So if there's a few slides that are, or more than a few slides in your opinion, that are too Juniper specific, I apologize. I tried to pare it down as much as I could. What else do I want to mention? I'll talk a little bit about it when I get into the signaling part, but if you've checked out the slides already, you'll notice that it's very RSVP heavy, again, because we're doing a demo and that's what we use as a signaling protocol. I'll talk a little bit about CRLDP. Personally, I'm agnostic. I don't think, I'm starting to get into the conversation right now, but I don't think there's enough experience with either in this application to, you know, determine whether one's better than the other. Who knows? In time, it might come down to the whole ISIS versus OSPF religious debate. So why don't we get going here? There's a few people coming in, but I think we got a full house, close to it, from my point of view anyways. All right, so the topic of the day, traffic engineering with MPLS. What I'll do is I'll go through the beginning of it as quickly as I can, again, knowing that there's a lot of slides so we can get to some interesting demonstrations. But I'll go over a little bit of history, get into some terminology with respect to MPLS. Many of you may be already familiar with a lot of this, so I'll try and go over it as quickly as I can. We'll get into some requirements. You know, what is this traffic engineering thing doing for us? And then we'll get into the good stuff. We'll talk about how some of the protocols have been extended to support this application. One of them being RSVP and the other one, the routing protocols themselves. And then we'll get into some features of the requirements of MPLS, like traffic protection and stuff like that. And that's about it for the agenda. Anything else? No, I think we'll move right along here. So we'll start off with a problem, say what are we trying to do? What problem are we trying to solve with traffic engineering? Why do we even need this? And I'll go through a bit of the history and hopefully we'll pop out the other end with a bit of an answer to that question. So as many of you in the room are probably aware of some of these details, you know, in the beginning of the internet, not really the beginning of the internet, but let's say the end of the last decade, or the 80s anyways, a lot of the networks were relatively small in comparison to today. The link bandwidths weren't that large, as you are all aware of. So engineering or controlling where traffic went in your network may not have been as much of a requirement as it is today. And so the IGPs that were used at the time, same ones that are used today, but they provided enough granularity with the cost metrics that they used to move traffic around like you wanted to. And here's a typical diagram of, you know, when you tweak an IGP cost, what happens to your traffic, right? So in this example, we have a green traffic flow going across the northern part of your network, let's say, and this is obviously a really small network. But when you tweak one of the costs on the links, you get this kind of snap effect. So it's not really granular traffic engineering, right? It's everything that was on the northern path is now following the southern path. So in a way it's traffic engineering because you've moved traffic from the top to the bottom, but it's not granular enough. You've moved everything. So if your goal in the first picture, I'll go back, was you noticed that the southern path was underutilized and you wanted to, send traffic over those links. Well, doing it with an IGP and just with the available metrics definitely moved traffic over the southern path, but now you're kind of in the same position where you have underutilized links on the northern path. So trying to traffic engineer with the IGPs alone as networks grew became much harder and harder and more complex, and it wasn't really deterministic. You could sit back and try and comprehend all the different scenarios that would occur with your traffic when you tweak the link over here, and then you go ahead and tweak it thinking that maybe you had everything figured out, and then once you change the metric, a whole lot of things happen that you didn't realize were going to. So it really wasn't granular enough, and it wasn't that deterministic. And it was also not topology driven, really. It was more just solely based on the IGP metrics. Or it was topology driven, it wasn't traffic driven, is what I meant to say. And that's what you're really trying to engineer, is the traffic over your given topology. So a little more about the history. As time goes on, the networks grow, the bandwidth grows, and this problem becomes more and more complex to solve with just, varying various link metrics in your IGPs. So here we're back at this question. There's a need for a more granular approach to traffic engineering. And I pulled this quote out of the requirements for traffic engineering. This was written, I guess, by some of the senior network engineers at UUNet a while back. And so basically what we're trying to do, why is it that we need traffic engineering? We're basically trying to maximize the efficiency with which we use the resources in our network. So ATM came along and gave us this capability, right? You could create VCs and engineer those VCs at that level of granularity. And not only could you engineer them based on link metrics like you could with IGPs, you could also take into account other constraints like bandwidth and stuff like that. So you had a lot more granularity, again, with which traffic went where and what constraints you could play with to force traffic over different paths. So this is what the typical scenario looked like. You had this layer 2/1 infrastructure in the middle, which were your ATM switches, and you were literally free to either to nail up PVCs anywhere you wanted to, or use some kind of ATM routing protocol at the time, many of which early on were proprietary. So this helps engineering traffic over certain links in your network, but it doesn't help the routers on the edge of your network, because as the top view grows in terms of connectivity and meshing, and if A, B, and C are your POPs, representative of your POPs, then this is the core of your network. You probably want a pretty heavily meshed network in terms of inter-POP traffic, right? If you're in a POP in San Francisco, going to, I don't know, so Dallas, let's say, you don't necessarily want to have to go through 3 other intermediate POPs through your network. So it may not be a full mesh, but it's probably relatively heavily meshed from a inter-POP perspective. So as that meshing increases, you have an issue with the IGPs themselves, because that layer 2, we'll go back here, that layer 2 infrastructure is transparent to the IGPs. You still, from an IGP perspective, have this large adjacency meshing requirement. So doing the overlay network and using ATM didn't really help solve that problem. It actually kind of, in a way, created it because you now have a heavily meshed network because the switches and the routers aren't peers in this network. They're kind of like ships in the night. So just a bit about the ATM path creation. You know, there was various mechanisms, some of which were offline tools that would just historically gather data, pull data off your ATM switches and, you know, build sort of traffic trends or patterns through your network, and would go out possibly and even reconfigure your ATM switches to optimize the network over time and continuously do this over periods of time. I mentioned a little bit already about these drawbacks to the overlay network, the fact that your IGP eventually runs out of steam if you're doing a lot of meshing because from the router's perspective, the switches aren't there and they have to keep track of these adjacencies and they get up into the hundreds. And not only that, Dave Katz will talk about this a little bit tomorrow, but you also have, you know, n cubed and n quarter, n to the fourth order of problems when links break and routers break, based on the way link state routing protocols work. So the overlay model kind of outgrew itself once it got really heavily meshed and there were a lot of nodes, router nodes on the edge of it. There's also the other drawback that, you know, everybody's been talking about for a long time is that, you know, ATM wasn't originally designed just for data, so you have all this cell tax overhead and stuff that is killing you. Like, well, what is it? TCP ACKs take 2 cells, even though it's only one extra byte or something. I forget the sizing, but anyhow, you have this extra overhead with ATM cells that you don't with MPLS. You have an overhead with MPLS, but it's not quite the same percentage. And also, the ATM SAR functionality required in the routers, not necessarily in the switches, but the endpoints of your PVCs. We're getting to bandwidths now in the networks where you don't see SARs being built to be able to handle these speeds, at least not yet. They're kind of falling behind, whereas ATM at one point was kind of ahead in terms of forwarding speed when compared to routers. The tables are slightly turned today, where you have OC192 forwarding capabilities on a router, but there's no SAR chip that I'm aware of that can do that. So that limits, another limit to the applicability of ATM to solve some of these problems. And this is back to the point where I said today you have, like, you know, routers doing line rate performance at higher speeds than ATM switches, and in a deterministic fashion when you're using an application like MPLS traffic engineering. So some of the benefits, I think I've probably touched on some of these already. The main thing, I mean, we're going to focus on MPLS traffic engineering today, but I think one of the main or strong benefits of MPLS is how it kind of decouples the forwarding plane and the control plane a little more, such that you can have the same forwarding mechanism, if you'd like, where you're doing label swapping, right? An MPLS packet comes in with a certain label, you do a label table lookup, and you swap the incoming label with an outgoing label. And regardless of your application, whether it be MPLS VPNs or MPLS traffic engineering, or at some point, you know, using MPLS for multicast traffic, that swapping function stays the same. Whereas today, with just kind of regular IP routing, that's not true. When you're doing IP multicast forwarding, it's very different than IP unicast forwarding. So I think decoupling these two functions more makes it easier in the future to develop new applications that will run on top of MPLS, instead of having to rewrite everything from scratch based on the requirements of this new application. Like, for multicast is a good example. I just wanted to mention the document if anybody's interested, and, you know, the next couple slides will talk about some of the requirements that have been voiced for any kind of traffic engineering tool that might be out there. So here we get into a little bit of details of them. So you need to, one obvious one is you need to be able to get traffic into these quote-unquote tunnels in the first place. It would also be really handy to be able to gather statistics on the tunnels themselves, the number of bytes and packets going in and out of a tunnel, so that you can do capacity planning and continuously tune, your MPLS LSP infrastructure over time to keep utilizing the resources of your network as efficiently as possible. You need to be able to characterize these LSPs. So we mentioned earlier that when you didn't have such a tool, you were solely reliant on one variable, which was link costs in the IGPs. So you need more granularity than that. So you have things like bandwidth, link colors, affinity bits they call them. You need to be able to prioritize these tunnels with respect to each other. So these are some of the fundamental requirements that were identified in the beginning of the whole MPLS story. So we'll quickly get into, I touched on a bit of the terminology already. We'll go into a little bit of it quickly, take a look at what a label actually looks like, and then get into some more interesting stuff like the demos themselves. So I mentioned that there is a little bit of overhead. You do have this encapsulation function that goes on, as you did with ATM, but it's simply a 32-bit sort of shim header that gets placed in front of the IP packet. So there's a lot less overhead, and MPLS is being developed over time with really IP data networks in mind, primarily. So this is what the label itself looks like. You have 20 bits for the label field itself. You have 3 bits for what they call an experimental field, which, as far as I know, most vendors today use it for doing QoS, class of service type stuff. You have a stacking bit, which allows you to carry a label stack. So an MPLS packet may be going through your network based on the top level label, keeps getting swapped, but there may be other labels below that may serve a purpose once the top label gets popped, they call it. Then you start routing based on, or forwarding based on the second label in the stack. Yes? That's a good question. Yeah, you would probably have to take that into consideration. I would expect, I don't know if I should expect, but I would expect that the vendor's codes should do that automatically, depending on the application. Right now, in today's environment, traffic engineering only requires the one label. There's the idea of nesting traffic engineering tunnels within each other that might take advantage of being able to label stack, at which point you might run into, you've reduced your MTU, your available MTU now because you're putting more and more labels along the path. I don't have any operational experience with that yet, so it's a valid point. I'm not sure how it's going to be addressed, either automatically by the protocols themselves and the routing code itself, or maybe you'll have to manually set. Probably not, I would imagine. Manually configuring anything on thousands and thousands of LSPs is not that much fun. So, but that's a concern. Yeah, it does reduce because the MTU. Well, and it depends on what MTU you're talking about. But if you're talking about link MTU, yeah, because this all ends up being put into, for instance, an Ethernet packet, right, or Ethernet frame. And Ethernet has no visibility, and it doesn't know that it's carrying an MPLS packet. Actually, it has an ether type, but it doesn't have the ability to extend its payload so that your IP packet can still be the same, even though you're stacking labels. I'm sorry, I should have repeated that. The question was, if you're stacking labels, how does that affect? Does that cause any MTU problems and any MTU issues? The short answer was, yeah, you're starting to chew up more of, for instance, the Ethernet payload for forwarding information, which leaves you less space for IP data, for instance. So your LSP has an MTU associated with it, and you probably have to take that into consideration. And I was just saying that today we only use, one level, so I don't have any operational experience with what those issues might look like. Yes? I'm sorry, I can't hear you. Yep. Sure. I mean, and the LSP itself carries an MTU as a variable of the tunnel, and you probably want to make sure that the MTU of the LSP is equal to the smallest physical or layer 2 MTU in your network that the LSP can traverse. Yes. Mm-hmm. Okay. I'm not here to sell traffic engineering. I'm here to talk about it. Okay. No, I'm not saying it's not a valid point. I'm saying I don't have the answer for you right now. I would imagine it would be automatic in the vendor code, but one, I don't develop the code at Juniper, and two, it's not an issue. Yes, I'm not familiar with what the answer is going to look like, but I would imagine, like everything else, it's going to be automated in some fashion. But I can't say for sure. I can give you maybe the email address of somebody at Juniper that could give you that answer, though. But then that's just Juniper, right? There's a whole bunch of other players out there. Anybody else in the room have maybe something to add to that, like one of the other vendors that are here? Yeah, and then that would automatically set the, okay. Yeah, Robert Razak from Cisco here. So one idea is that you could use MTU path discovery to discover what the MTU should be for the LSP. Yes?
Again, the point here is, well, what type of solution does this? If someone is trying to help with this book,
Okay.
so far I think it is no solution.
Okay. So you're saying if you were, for instance, selling an LSP to a customer, their MTU requirements might be different than your own internally within your own network.
You have to provide the way for customers to use your network.
Okay.
You can't say you can do this. You have to provide the way how to do it.
Okay, well maybe I'll come back to that at the end. I'm kind of at a loss right now to have a good, solid answer for you, but it's a valid point. So I shouldn't have even mentioned the stacking bit. Just kidding. We also carry a TTL field as well that by default is copied from the IP. It's carried over from the IP TTL field. So your trace routing and stuff will still work through an MPLS tunnel. And we'll see later on that there are features to turn that off if you wish. So here's just a typical path through a network based on an IGP. These routes may be learned via BGP, but then you resolve the BGP next hop to some IGP route through your network. What MPLS allows you to do now is to send maybe some of that traffic through a different path of your network. And you can bind, they call it binding, you can bind prefixes to certain LSPs. So maybe 192.168/24 uses the regular IGP path, but then 134.112 uses this tunnel. So you need to have this granularity to be able to pick which traffic uses which tunnel. This gets back to mapping traffic into a tunnel and binding prefixes to LSPs. Did I skip something? Oh, the point I wanted to mention, because it's in red, is that these, like ATM PVC, these LSPs are unidirectional. So if you want to traffic engineer in both directions, you have to go on both ends and set up LSPs in either direction. And LSPs, I keep saying it, and I haven't gotten to the vocabulary yet, but just in case some in the audience aren't familiar, it's label switched path, basically, or swapped path if you prefer. So the tunnel through your MPLS tunnel through your network. I already mentioned the basic mechanism, how this works. An MPLS packet comes into an MPLS router, it looks at the incoming label, which references a table that tells it which outgoing interface and which outgoing label to use. So you're just swapping labels through an MPLS domain. You're not looking at the IP header information at all. And these LSPs, as we'll see later on, can be set up statically, nailed up like you could with ATM PDCs, or they can be signaled. And even within the signaling portion of it, there's some granularity. It can be signaled based on constraints, or just based on where the IGP would have gone anyways. And here's just an example of how, I think the next one's actually an animated example of this. Let's see if it works here. Oh yeah, okay. So the IP packet comes in, and that's the destination address, 134.112.1.5, and somehow you've bound that 134.112 prefix to this tunnel. So that's what gets the IP packet into the tunnel in the first place. So you encapsulate the 1965 label on it. Santa Fe swaps it to 1026, and then on the last leg, it's swapped to label 0, and then the egress router pops the label. And we'll get into details. I think we might have a slide on this. I can't remember, but the last link there are certain labels that have reserved meanings in the MPLS specs and drafts. And label 0 specifically tells the router that takes in the packet that has label 0 to pop the label and start forwarding it based either on IP, because there are no more labels, or if it pops the label and there's a label under it, it'll forward on the second level label. There's also another way to do this. Label 3 has a special significance as well. If the egress, in this case New York, tells the upstream router, I don't have a city name for it right now, to use label 3, that means the penultimate hop will pop the label. Penultimate meaning the one right before the ultimate, the egress. So basically the difference is you're popping the last label in different places, either the ultimate, the last node of the tunnel, or the one just before it. And labels 0 and 3, that's the distinction between the two. And it's during the signaling of the setup that the egress tells his upstream which label to use, either 0 or 3. And we'll see that coming up in a few slides. So here's our example topology. This is physically how these PCs here beside me are set up, and the IGP link costs, the loopback addresses are there, and here's some of the IP addressing. So all the demos we'll be doing today will be on this topology. It's not a sexy topology. It's probably not even a real topology. It's just, we kind of plug these in ad hoc, and this is what we came up with.
You might want to dog-ear that page also, just so that you can reference the addresses that we're using in the demos.
So I think we get into some signaling here. So I mentioned you can do set up these tunnels statically or via signaling methods. There's obvious drawbacks to doing it statically, just like in the ATM world, where you manually have to configure every router along the path, and if things were to break, there's no rerouting around it because these are nailed up. So if a link breaks, you have to go to that router and manually point the LSP in a different direction. So your reconvergence time is probably really, really high in that scenario. Whereas with signal LSPs, you just configure the head end, have the head end signal the LSP through the network, and should a link fail anywhere along that path, because you're using signaling, the LSP can recover and reroute. I talked about this a little bit already. We'll get into some of the capabilities of RSVP, where you can do strict routing through your network or loose routing. I'll wait till we get to those slides. Basically, by default, the original RSVP spec, it was designed for end host applications to reserve resources from a network. And originally the way RSVP would work is it would be forwarded along the IGP path. So it's not a routing protocol or anything like that. It would rely on a routing protocol to get to the end node. So there'd be this hop-by-hop processing of your RSVP packets. And we'll see coming up that to support traffic engineering, RSVP has been extended to kind of do source routing of RSVP messages. I'll wait till we get into the extensions, but as I said before, the extensions we're about to go through with RSVP have also been added to LVP. So originally, you didn't have the capability with LVP alone to, for instance, talk to a neighbor that was multiple hops away, because you're probably wanting to establish tunnels across multiple routers, right? You couldn't do that with LVP. You also couldn't carry the attributes with which you want to constrain your LSPs with LVP. So CRLVP allows you to do some of these things, and similar extensions are made to RSVP, because originally RSVP couldn't do this either. It couldn't do source routing, for instance. You couldn't tell it where to go through your network. It just followed the IGP by default. So I don't have a whole lot on the details of CRLVP, and I don't want to get into the rat hole of comparing the two protocols. Just know that both have been extended to carry these extra attributes you need to do traffic engineering, and to do this kind of source route functionality where you can bypass the IGP. Whatever the IGP route is, you can ignore it and take some other path through your network. So it gives you that control over where traffic goes through your network. There's a big debate as to which one's better. Like I said earlier, you have very smart people that are opinionated on either side of the camp. In my opinion, there's not enough operational experience to draw any conclusions yet. Most implementations running networks that I know of use RSVP for the signaling method. I don't know that means it's better. It just means it was ready first. Operational code was ready using RSVP before CRLVP. I think only time will tell if one is better than the other, or if not. Like I said, it might end up being an ISIS versus OSPF thing. I don't know. I already talked about this. Okay, I'm getting ahead of myself here. It's RFC 2205, if anybody's interested. So basically, let's look at how RSVP signals these things. So RSVP there's several types of messages within RSVP. You have path messages sent from the head-end router all the way down to the tail-end router, so downstream, requesting that those routers along the way, reserve labels and stuff like that, and indicating what constraints you're looking for. And on the way back, you have reservation messages that are actually nailing up these resources in the routers on the way back. So here are some of the messages. On top of the path and reservation message, you have a path tear and a reservation tear. Should anything, for any reason, the state in your RSVP session change, you want to tear down that state along the routers in the path, even if you're building a new path. So that's what some of these messages will be used for. You also have the capability to report back errors. Should a link somewhere in the middle of an existing LSP break, RSVP can signal back an error message to the head end, so you can reroute. And you have these tear and error messages in both directions, because like I said before, it's unidirectional, so path messages literally flow from ingress to egress, reservation messages in the opposite direction. So we'll talk a little bit about the extensions made to RSVP to support MPLS traffic engineering. One of them is the ability to even carry labels. There were no objects in RSVP originally to be able to carry the MPLS labels that are required to forward traffic. So here are some of these objects we're talking about. You have the label object itself, you have an explicit route object, and that's the object that allows you to do this source routing I keep talking about. So the head end of the LSP tunnel basically uses whatever algorithm, CSPF for instance, constraint base, shortest path first, to build this ERO, which it then gives to RSVP that goes off and signals this through your network. So before this explicit route object, RSVP messages would just follow the IGP through your network. Now you can tell RSVP on the head end, these are the nodes you have to go visit through my network. Then you have the label request object that path messages are sent down from ingress to egress, requesting routers to reserve labels. And then on the way back, the reservation messages will actually carry the label objects. So it's downstream allocation in the sense that it's the egress that tells its upstream neighbor what label to use when sending it a packet. And then you've got the session attribute and tspec objects, which carry the variables and characteristics of the LSP you're trying to set up, like bandwidth, affinity, class, the colors we'll talk about later, so on and so forth. So just some more details on each object itself. I already mentioned a little bit of that explicit route object. You can have, this object can be loosely routed or strictly routed. So in other words, you can specify in this object every single router node that has to be visited through your network, or it can be a loosely routed RSVP message, which means you can specify you have to go through this node in Denver, but between here and there, just follow the IGP. So I want to go from San Francisco to New York, but you have to go through this specific IP address in Denver. So between San Francisco and Denver, you follow the IGP, and between Denver and New York, you follow the IGP path. So here's an example of a strict. So this ERO object's been fully populated in this case. So you've told the RSVP protocol on A that you have to go through B, then C, then E, then D, then F. E, then D, then F, yeah. Alternatively, like I said, you could do a loose strict route. Loose strict route, that doesn't make much sense. A loose route through your network that says you have to go through D. How you get to D, is kind of up to you, which means it's up to the IGP. So B, the RSVP message comes into B, and he would forward it based on what his IGP tells him is the best route to get to F. Or sorry, to get to D in this case. Any questions on that? That's clear? Okay. And you can combine the two. So you just tell RSVP you have to visit this node and this node, but between those two nodes, let the IGP go and tell you where to go.
Is the RSVP being used for bandwidth reservation as well as function?
Yeah, this is one of the constraints, which nodes to visit through your network. The other constraints we'll get into are like bandwidth and link colors.
So in all this, the administration of the NANOG and strict source route, how do you keep track of the overall of what you've done, having the history? If you've done a lot of manual administration, in a large network, how do you ever administer that?
Well, the ERO is manual. It can be manually built, but more likely you'll let the constraint-based routing algorithms build it for you. So you won't actually manually say you have to go visit these nodes. You'll place constraints on the LSP, as we'll see in a few demos. You'll say, I want an LSP from San Francisco to New York, and I want it to be 70 megs, and I want it to use green links, and you give it all these constraints. And we'll see in a little shortly how the routing protocols have been extended to carry these extra bits of information around so that A has all this locally in its database, and it can decide automatically based on the constraints you want for this LSP what is the best path. So it'll automatically build the ERO for you.
One other thing.
Sure.
So if you try to do a strict, and then you build a bandwidth system there, it automatically go back to loop.
No, if you're manually doing strict, it's because you want it to use that node. If the bandwidth isn't there, if you're also specifying bandwidth and the bandwidth isn't there to use, the LSP probably just won't come up. And again, that might get more into kind of vendor-specific implementations, but that would be, you know, my guess, because the way, you know, basically what you're telling RSVP is you have to send this message through this router, right? If there are multiple ways to get multiple links to the router, and one of them supports the bandwidth, it'll go. If one doesn't, it'll probably fail and won't get built. Okay? So our first example, our first demo. All right, I can stop talking for a change. So we're just basically going to build a simple, loosely routed LSP from router A to router D, and I can't even remember which node we specified it has to go through. Do you?
It's router G.
Router G.
Over here. We're going to specify a loose route through router G. And maybe just as a quick overview, just about 20 seconds worth, so that you know what, so if we're all on the same page of what I'm doing on all these demos. We've got the router prompt here, and you can see router A in this diagram. This is the router we're on right now, which is sort of a user mode is where we are right now. We can go into configure mode, and from there you can show the entire configuration if you want. The way the configuration is broken up, there's different how would you say that? There's sub-portions, hierarchies within the configuration for interfaces here, routing options, protocol, and policy options, so forth. You can focus in on certain parts of that configuration, and the reason I'm pointing that out is because that's what you're going to mostly see me do as I demonstrate things. For instance, I can say show protocols, and it'll show me all of the RSVP, MPLS, BGP, ISIS configurations. I can also do a show protocols, MPLS, and look at just the MPLS part of that. And that's actually where I'm going as the first example. You can see right now that the only thing that's running at this point on router A is the little statement under there that says interface all, which basically is turning on MPLS on all interfaces. And my apologies to the people in the back of the room. It seems like all the commands are going to come up at the bottom, so hopefully that's not going to be too difficult for people. So this is pretty much at this point the same configuration that's on every router. Basically, we've just turned on RSVP and MPLS on all interfaces. We're running BGP, we're running ISIS as the IGP. So the first thing I'm going to do is just, and you're going to see this throughout this presentation, we're going to be loading in some pre-canned configs that we wrote ahead of time, just so that we don't torture you with a lot of configuration steps. So I'm going to put, whoops, and if I was a competent typist, it would be a lot more interesting. But first thing we're going to do is load in a config here. And now, if I do a show protocols MPLS, you can see the config that I'm loading in. What I've got here, and you can compare that to what was there, which just showed turning MPLS on. And again, this is at the ingress router. I'm defining an LSP, and I'm giving it a name, A to D. It's an arbitrary name that means something to me. It's an LSP that's going to go from router A to router D. And we define where the egress of that LSP is. In this particular case, it's the loopback address on router D over there, which is 192.168.24.1. And that will pretty much through all of these examples be the egress router of the LSPs we put up. We next define the path that that LSP is going to take. In this particular case, we say, and we only have a primary path, there are no secondaries at this point. So our primary path is something that we've named through G. Again, it's just an arbitrary name that we gave it. And down here is where we define what that path is. Through G, and here's the loose constraint that we put on. We said that we want it to go through router G, and the router ID of router G over there is 192.168.12.1, and we want that to be loose. In other words, we don't care how it gets there, it's just loose. The last part of that is less interesting at this point, but Chris has talked about constrained shortest path first, CSPF. At this point, we've got it turned off. That's what that no CSPF does. So we're manually telling RSVP what constraints to signal through the network. So I'm going to, at this point, these configurations haven't taken effect, so I'm going to type commit.
Go ahead, what's your question?
Constraint sounds like that there's, some type of limitation, here you're making primary HPG.
Yeah,
Right.
it's a little confusing. Yeah. Making it go through a certain router is a constraint, right? I guess the difference, one way to look at it is, it's not the constraint-based shortest path first algorithm that's building the ERO, right? So we are applying a constraint to this LSP, right, that it has to go through this node, but it's the regular IGP routing table that's going to be used to forward the RSVP message along, given this constraint. Whereas we'll see coming up, when we turn on some other constraints and basically turn on CSPF, where the head end will calculate the entire path, and it might be something completely different than what the IGP would have taken, based on the constraints. Is that clarified a little bit? Okay.
Yeah, and I think your use of the term limitation is exactly right. If I did not define this constraint right here, basically that LSP would just follow the shortest path defined by, in this particular case, ISIS. But I've given it a limitation. So from there, and by the way, this is the only place this configuration is put on, is that the ingress, this ingress router will use RSVP to signal across the network and set this LSP up. So if I do a run show RSVP session detail, here's my RSVP signaling. And you can see I've got one session set up, and there's some interesting things in here. You can see that a path message was sent to 10.0.15.1, which is the next hop router, that's router F down there. I also received a reservation message from 15.1, and of course these are actually ultimately going to and from the egress router. But what's mostly interesting is this. Here is my explicit route. Right, I'm going to 10.0.15.1. From there, I'm going loosely to 192.168.12.1. The record route object, Chris talked about the RRO, the recorded route object, and this is very useful, by the way, for troubleshooting.
Actually, I forgot to talk about it, I think our slide missed that.
No, you mentioned it.
Did we?
Yeah. Anyway, record route object. You can see here, if you look at the addresses, that the first hop of that LSP is router F, and it's the interface there is 10.0.15.1, which is shown here. 10.0.13.2 is the next hop, which is router G. So it gets to router G based on how ISIS has told it to get to router G. And then 10.0.31.1, which is the interface of router D on the egress. The other things of interest here, and I'm not going to do this every single demonstration, but I want to go from one router to another and show these particular features. Here, obviously, there's no label going in because this is the ingress. Yes?
You have multiple links between give it two routers, just to understand, for example, like for backup load sharing between two routers?
Yeah, there's several different flavors of that, and we actually have a demo of doing that if we get the time to get to that demo. We'll actually show how to do that. So at the ingress, obviously, there's no label coming in. Going out, we've set a label, and this, again, is automatic. RSVP has signaled this, a label of 100,030. And at this point, I'm going to move in a real high-tech way here. I'm just going to flip my cord to router F.
But let me, the record route object, just because I don't know that I mentioned it, Jeff touched on it a bit. It's basically different than the ERO in the sense that the ERO, the explicit route object, is calculated or can be calculated, fully populated by the head end router, which tells RSVP where to send the message, right? But the state in your network or the links in your network could change while you've sent this RSVP message out, such that there's no longer, for instance, a path between router F and router G. That link is down, right? So the record route object, what it's doing is it's actually kind of a live snapshot of what routers were visited by the RSVP message. So each router that this RSVP message ends up really getting sent to gets tagged into that record route object. So it helps for like loop detection and stuff like that. And it's really, really neat for troubleshooting. So,
The other assumption here is that this is all one AS.
yes, yes. The second AS is up in the corner there. But it's mainly going to be, because today it's pretty much only done, as far as I know, within a given AS and domain. So we're not going to talk about MPLS traffic engineering today, even though it's a pretty interesting topic. Yeah.
Is that link state based or is it like some sort of hello people on sign?
With the RSVP messages?
Yeah, your path.
The path itself is fully calculated from the head end based on link state protocols, yes. But the messages themselves just follow sort of the source route they've been given. So it's in the message itself which path to follow. The explicit route object is carried in the RSVP path message. Does that answer your question?
When we get to the example of actually using CSPF to do these calculations instead of just prescribing them on the ingress, if I don't remember to show it, please remind me, and we'll look at the ISIS LSP, and you'll see where the extra TLVs are added in there that allow these parameters to be carried within ISIS.
When something breaks, how does some of the path change initiate?
Yeah, the next slide will cover how we find out about when a link breaks. I was kind of, with the record route object I was mentioning, there's a real-time difference, right, between when that link breaks between F and G and when A finds out about it. So if he doesn't yet know about it, he may build his explicit route object thinking that link is up and send his RSVP signaling out, right? The record route object will then actually record what real routers you actually did touch with this RSVP message. So it's giving you some feedback that you might not know ahead of time. It doesn't do anything for routing the objects or the messages themselves. It just is literally like a record route on a ping, for instance, right? It's giving you exactly where this message has gone because it might have encountered a loop even though the head end wasn't aware of that loop in your network yet. And we'll get into how that happens. And
what we've got here is you can see right down here at the bottom, we're at router F, which is the next router along the way. And kind of scrolling back, here is what we just displayed a while ago from router A. And you'll notice here it shows that this particular session is at the ingress. And at router F, it's showing that this is a transit session, obviously. It's neither the ingress or the egress, it's transiting that router. Again, you've got the record route objects, you've got the ERO here. But what's interesting here is, again, scrolling back, if you look the label out here, it's 100,030. Whoops, sorry. The label in on that path here is shown as 1,030. The label out, it has swapped labels there, is now 100,044. The other thing that's interesting here is notice the LSP name is recorded at the transit router. The transit router is not configured with that name. The name is actually carried in an ASCII field in the RSVP messages. So this router has learned the name of that LSP through RSVP. Switching again to G. And we'll do the same. We'll look again. Here we are at G. And again, we've got an LSP, the same LSP, A to D. That label that was added by router F, 100,044, is now shown as the incoming label there. And we swap again because this particular router, router G, is the penultimate hop, the penultimate LSR in this LSP. So the outgoing label there is going to be 3.
So just to remind the audience, in this case, because router D has told this router G, to use label 3, there's a special meaning for label 3, and it tells router G to actually pop. So you're not actually swapping label 3 onto the packet going out the interface. You're actually popping the last label and just forwarding it as an IP packet. So it shows up at router D in this scenario, goes into router D as an IP packet.
What's the functional reason for doing that? What's the desired effect? Like, what is the desired?
Yeah, one application I can think of is if you're doing label stacking, and you want the penultimate to pop one level and the ultimate to pop the next level. Robert, can you? Anything else? Okay. That's one application. There may be others I can't think of off the top of my head. Oh, okay. Theoretically, yeah. I don't know of an application yet for 3 or 4 levels of labels, so it's hard to answer the question without understanding how it's being used. But theoretically, and I'm sure, you know, your code implementation could also pop both levels on one router, right? It's not that you have to do penultimate and ultimate to be able to pop 2 levels in a stack. There just may be, it may be efficient in your given router implementation or code implementation to do it that way, so it's nice to have the option. The question was, I think, referred to that as, well, what's the benefit of doing one versus the other? And I think, I don't know that there's inherently any benefit. I think it has to do with how you've implemented this functionality in your router code and in your router hardware. Doing it one way versus the other might help your particular router, you know, forward quicker, or it might not. I don't know. I'm just thinking of the reasoning behind it. It's nice to have the option. You need a way to distribute all these new attributes on which you can route traffic through your network, and the IGPs have been extended to do so.
And the camera's back on now. So here we are at the egress router. Notice the RSVP session shows that this is an egress RSVP session. And the incoming label here was the label 3. I'll label out obviously as nothing because this is the egress. So that's about all on that particular example. But going back again to router A here, one of the, let's see, another thing I might show is that what we've been looking at is the RSVP session. You can also do a show MPLS. You could, if I could spell, LSP. And this shows you the actual LSP that's brought up. And again, in the messages here, you see the record route message. And I think on the next slide, as Chris said, we're gonna give an example now of setting up a strict path. So to do that, I'm just gonna load up a different config, and this is, let's see, here it is. I'm gonna commit that, make that take effect, and just to show, this is how the config changed. We've still got our LSP named A to D. It still goes to the egress router of router D, which is 192.168.24.1. The primary path that we specified, though, has changed. In this particular case, we specified a primary path that we gave the name strict to D. And down here for path strict to D, you can see that we specified a strict path. And on the slide over here, it shows what that path is taking. We're using all router IDs here, 192.168.8.1, which is router F. We go to router G, which is 12.1. We then go to router E, which is 5.1. And then finally router C, which is 2.1. So if we again do a show RSVP session detail, here you can see the explicit route that we specified, and below it is the RRO. Notice the explicit route is actually using router IDs, but the record route object is using the addresses of the physical interfaces that are being passed through. And let's see, and then again we can do a And again, here's the actual LSP that's brought up. And once again, you can see the record route. It's kind of running off the screen there. There's the rest of it. And let's see.
I think that's about it.
That's about it.
Yeah. So we haven't, besides telling the LSP exactly which nodes to visit, we haven't yet specified any other constraints. We'll get into that shortly. So I talked about this already, the hop-by-hop ERO processing by default if you haven't, so it's basically source routing the LSP from the head end. This is a label object I talked about earlier. The label request object is carried downstream in the path messages to tell routers, hey, I want a label, please set one aside for me. And on the way up, on the way back in the reservation messages, the routers tell the upstream router exactly what label to use for this LSP. This is why I didn't talk about the record route object. We didn't get to the slide yet, but I've already mentioned it, so let's move on. Same record route object, but in the opposite direction for the reservation message on the way back. Here's the object that carries some of the attributes we've been talking about. We'll get into what some of these mean later on. The ASCII character string we mentioned is carried in the session attribute object. The ability to preempt existing LSPs if you chose to do so. Then you have the tspect object, which specifies the bandwidth you want to use for this LSP, or you want to reserve from an RSVP perspective. Here's just a quick visual on the path message and then the reservation message coming back. So it's on the way back that the labels are actually nailed up in a sense. New York tells Miami, use label 3 meaning pop. And then Miami tells the upstream node, use label 1026 whenever you're sending me an MPLS packet on this LSP. So some other additions that have been made to RSVP to help scale it more, so you could have, you know, a great number of LSPs running through your network. One of the things is an RSVP hello mechanism, because I think I failed to mention as well, the state that RSVP sets up through your network is periodically refreshed with those path and reservation messages we just saw. Those timers are typically by default pretty high. I think on our box it's every 30 seconds you send out a path message to refresh the state, and I think after about 4 or 5 times that number, you consider the state dead if you weren't successful getting these path messages all the way through from end to end, or reservation messages. So that's not really doesn't provide really that quick of a reconvergence mechanism with those types of timers, and also it's on a per LSP basis. So you're sending these path reservation messages for each and every LSP that's set up in your network. Whereas this mechanism is a little different. It's between neighboring routers, and it's just to track basically the state of the link and the neighbor that's, you know, right beside you. So it's a quicker way, and it applies to all LSPs. So you're not really, it's not tied to a particular LSP, it's tied to a particular neighbor. And the timers you can see on this by default are a little much shorter.
So you're saying don't go down the path reservation?
Yeah. Yeah.
So do the labels ever change? Like the routers girl out there already have this label, some name label that you gave it.
Mm-hmm.
They never change the label.
No. Yeah, this. Let me give you the answer. I'm hoping it answers your question. I don't know if I fully got it.
When you send subsequent path reservation,
Yep.
are different labels every year?
Oh, no.
They always maintain those labels.
They're always maintaining the same labels, yeah. Sorry. Another thing that's been added is the ability to aggregate messages, path and reservation messages. So you may have, 1,000 LSPs going across the same physical link in your network, where you can turn this type of functionality on to aggregate all those path messages in a bundle, if you want, a bundle PDU. So across that OC192 link between two routers, instead of sending, 1,000 path reservation messages for each LSP that's established, you essentially bundle them all in one. So you're tracking the state of all of them in one message.
And roughly how many bytes?
Oh, that's a good question. I don't know. I'm not sure. The unbundled ones are typically 100 or so bytes, depending on how many hops in your network. The bundled one, I'm not sure off the top of my head. Sorry. And on our box, it's disabled by default, so it's a knob you have to turn on. Okay. So now we'll get into some more interesting stuff, actually what we call constrained, meaning with the bandwidth statements in the colors. So what we were previously doing, we refer to as signaled LSPs. You're still using RSVP to signal them, but you haven't yet specified any constraints beyond the sort of what node you have to visit type thing. Now, with constrained LSPs, you actually are using an extended SPF algorithm, which is similar to the regular SPF algorithm, except that it takes other things into account now, like bandwidth and link colors and things of that nature. We'll also get into how the IGPs had to be extended as well to distribute that information around. So in the case of constrained LSPs, at the bottom of the slide, the head-end router is building the complete ERO, so the complete source route for the LSP, based on the constraints you've given it. As I mentioned, it's just a modified shortest path first algorithm. It's just smart enough now to look at other variables than just link costs. I'm using the terminology color. I think the drafts actually use affinity class. It's just a way to identify a link, if you will, color it, tag it, use whatever terminology you want, because you may want to avoid certain links in your network or to include. So, yeah, it's just another way to identify it. It's kind of an administrative thing, an administrative knob you can play with to say, this really important LSP should never use this link, for instance. And here's some of the extra constraints with this extended SPF at the bottom of the slide. Hop count, bandwidth, strict or loose routing we already talked about, and these administrative routes, which basically refer to the colors. So this is how you compute the ERO. You build this traffic engineering database based on what the IGP floods around, and we'll get into those extensions again. And so the head-end router has this traffic engineering database. So it has all the link variables in your network local in some kind of database. And so CSPF will use that information and the information you've configured on the LSP, like what constraints you want this LSP to meet. It uses those two pieces of information to ultimately come up with the source route through your network. It builds that ERO, hands it off to RSVP, and then RSVP goes out and signals it, just like we just saw in a couple previous slides. So let's look at this traffic engineering database. It's very similar to the existing link state databases, and is actually populated with the existing link state protocols. It just carries extra bits of information. And it is separate from the regular IGP database because you have both of them held in memory, because you might not be forwarding all your traffic through an MPLS cloud, so you still actually need an IGP. You can't just, MPLS isn't there to replace your IGP. It depends on the existence of your IGP. So here's how they've extended the two main link state protocols, ISIS and OSPF. Basically in ISIS, the information about your topology is carried around in what are called TLVs, type link variables, values, or CLVs, code. I think they're called code in the ISO spec. I can't remember. But anyhow, little bits of information that are carried in ISIS link state packets to describe the state of the links and nodes in your network. So they've added TLVs to ISIS to be able to carry the RSVP bandwidth of a link and the color of a link. No, this is in the drafts, the extensions to the, I don't know that it's made it to, RSC standard yet, but it's been in the drafts for some time. So it's not, iOS has this as well. Anybody that runs or has MPLS traffic engineering code would first have to have this type of extension to their routing code. And it's not Juniper specific. So they've added TLVs to ISIS, and then on the OSPF case, because it doesn't use TLVs, they came out with the new LSA, and they decided to use the Type 10 opaque LSA, which has area flooding scope, so it's not flooded outside of an OSPF area. And basically that LSA carries the same types of information that the extra TLVs in ISIS carry. And we'll look at what that is here. So one of the TLVs, the new TLVs that have been defined, is a new IP reachability TLV. There's an existing one with ISIS. This is just another one with the same name, but it's been extended to be able to carry wider metrics, because originally in ISIS you were limited to 6 bits for your link metrics, so you couldn't configure anything more than 64, which kind of limited how much granularity or flexibility you had with defining link metrics. So this isn't really pertinent to traffic engineering itself, but since they were extending it anyways, they took the opportunity to widen the possibility for link metrics in ISIS. They also took advantage of the opportunity to allow inter-area, or I shouldn't say area, I should say leaking routes between levels in ISIS. So prior to this, if you were running an ISIS network, all your level 1 areas were kind of like stub areas. They just sent traffic to the closest level 1, level 2 router. You didn't have specific information about prefixes that lived outside of your level 1 area. Now we added this up-down bit so we can track when routes have been leaked from the backbone down into an area, so that when they come back around, we don't leak them back into the backbone and have this sort of routing loop of information. So prior to this bit, you couldn't do this in ISIS. Again, this doesn't have necessarily anything to do with traffic engineering, but it's an extension that was made to ISIS at the same time. The extensions that do have something to do with traffic engineering are the sub-TLVs that were added to a new IS reachability TLV. And the sub-TLVs carry some of the attributes we've been talking about, like the maximum link bandwidth on any given link, the maximum reservable link bandwidth, because you can have a given, like, let's say it's a fast Ethernet, it's 100 meg of link bandwidth, but you can configure RSVP to either oversubscribe or undersubscribe that. So you can say 50% of that is available to any RSVP session, or you could say 200% is available. So that's where the maximum reservable link bandwidth attribute comes into play. And then you can also assign a traffic engineering metric that's different than the ISIS link metric if you choose to. The administrative group refers to the affinity stuff I was talking about, the color of the link. And then there's some more reserved sub-TLVs for future expansion.
Here's an example of an ISIS LSP up here that is pulled out of the database. And if I scroll down a little bit, you can see some of these extensions. Reservable bandwidth. We'll talk about all of this a little bit later, but metrics: reservable bandwidth, maximum reservable bandwidth, and administrative groups, which you can see here is none, that sort of thing.
In ISIS, we'll see. I think I've got a slide on that. Yeah, the Type 10 LSA basically carries all this information as well. I believe both, I know Junos does, and iOS probably does as well, have working extended OSPF code. Originally, this was all done in ISIS first because the networks driving this technology were the tier ones that were only running ISIS. So the ISIS work was kind of a little bit ahead of the OSPF code. But today you can run either protocol, and you should be able to do traffic engineering across either. So now we'll set up an LSP and actually ask it to chew up 40 megs of bandwidth across the northern route of our network.
Okay. And what I'm going to do here is another config, which is, I have to look to remember what the names of these things are. And what we're going to do before I commit it, here's the new config down here. And you'll notice there's not much to it. All we're doing right now is, again, we've got the same LSP defined with a name of A to D. We want that LSP to go to 192.168.24.1. The only constraint we've given it is that we want to reserve 40 megs of bandwidth. This example network we're using fast Ethernet interfaces through the whole network. So all of the links physically are 100 meg links. We're going to reserve 40 meg of bandwidth for that link. The last piece to notice is, if you recall from the previous config, there was a keyword down there that said no CSPF. That's gone. We're running CSPF now. So I'm going to commit that. And now if we do we can see our LSP has come up, and notice up here it shows we've got we're reserving 40 meg of bandwidth. And in our record route object, we can see that it's taking this kind of northerly path here through 192.168, 192.168.0.1, but the physical link is 10.0.16.2. Then the next stop is 10.0.11, and then 10.0.24.2, which is the egress router. Of particular information here, or of particular interest, is if we can look at the different data entries in the traffic engineering database. And as Chris said, traffic engineering database, everybody here has worked with OSPF or ISIS or both, and is familiar with link state databases, and that's really all this is just another link state database. So if we do a show TED database, we can get a brief listing of all of the entries. And by the way, these entries are being taken out of the ISIS LSPs, the TLVs that are pertinent to traffic engineering. So to look at a specific one, we want to look at an entry that's come from router C, which is the penultimate hop router there. So we're going to do the same command and do, let's see, router C. And what's interesting here to notice is for available bandwidth. And this is the link 10.0.24.1. Looking back at this diagram, you can see that that's the link that's facing the egress router. Again, the reservations are being made from the egress router back to the ingress router. So the reservations were always on that interface towards the egress router. And you'll notice that we're showing 60 meg of bandwidth, reservable bandwidth. So we have reserved 40 meg of bandwidth. Let's see. And if we do a trace, yeah.
Sure.
Before, when you showed the display that was vertical, that showed you two classes, 182. I thought that there was probably like some type of quality service like class, but now I see that you reserved 40 before you reserved them all classes.
Yeah, we'll get into that. That has to do with the priorities you can assign, preemption and setup priorities you can assign to LSPs. So you have, in Junos anyways, you have 7 or 8 levels. So it has to do with preemption. You can assign different setup priorities to LSPs such that if you want to build a new LSP and it has a higher priority, it can preempt and bump another existing LSP if you choose to do it that way. And so these 0 through 7 are showing you what's available to each priority. And so if I come in with a setup priority, let's say of, I don't know, 3, everything 3 and how does our number system work? Yeah, everything 3 and above numerically is considered weaker, if you will, as an adjective. So I will nail up 40 megs at the level of 3 and everything below, but levels 1 and 2 still have 100 megs available, meaning they could preempt me. If an LSP came in with a setup priority of 2 or 1 or 0, it has more RSVP bandwidth available to it and it can preempt me. And it may not preempt you, it depends on how much bandwidth you're looking for, but there's more bandwidth available to those more preferred LSPs than to my LSP, for instance. So that's what that's tracking. No, the default is actually the lowest, which is 7. Highest number, I don't know why they did it this way, but highest number, weakest setup priority. And we have slides on that, we'll show you.
Yeah, and what we're doing in our configuration here, from this picture over here, we're calling that small net. We're dumping a bunch of BGP routes into our domain. And so I'm going to trace to one of these BGP routes. They're all 134 something, I believe. And you can see on this trace route that we're taking this LSP to reach the destination here and on the next hop. And then, of course, at 10.0.24.2, that's an egress router, so the trace route at this point just looks like a regular IP trace. But the first 2 hops are going through that LSP.
So Jeff's tracing to this interface right here, right now. This interface on router Y connected to router X, that's the destination of his trace route. So the last 2 hops are just IP forwarded packets. That's it.
Okay. Yeah, and we'll go to that next slide.
Next slide, we'll just build another LSP. This time, one thing I'll mention though that may not be obvious in this slide is everything, when we haven't set up any LSPs in this particular network, there's 100 meg available everywhere. So why did it choose the northern route? Well, I don't have the costs on this particular diagram, but if you go back to the original diagram, one of the other attributes, as is always carried in IGPs, is the link cost. So this is the lowest end-to-end IGP cost to your network that meets the constraints of the LSP as well. And I mention that because down here, we're setting up an LSP2 with 70 megs, and if LSP1 wasn't already there, LSP2 would also go across the northern path because it has a shorter IGP cost. But LSP1 is there, and by default, we don't allow preemption, so the northern path may have a shorter IGP cost associated with it, but it doesn't meet the constraints of this LSP because there's only 60 meg now available on all those links. So I can't use that. So now I use the next best IGP costed path through my network that meets the constraints. And that's why now I go along the bottom. So any packet that was IP forwarded using the IGP route from A to D would go north. But if I'm sending packets, if I'm forwarding those packets based on MPLS, it may go south. So it may diverge from what the IGP would normally have done. And this is an example of that.
What I've got loaded here is just another config, and if I now do a show protocols in MPLS, you can see that I've now set up 2 different LSPs. The one that we had before, which is A to D, requesting 40 meg of bandwidth. We've got a new one called second A to D, and that one is requesting 70 meg of bandwidth. And as Chris said, if you look back on this display, again, this is at router C, we've only got 60 meg of reservable bandwidth left on that interface. We're asking for a reservation of 70, so obviously we can't set up that LSP through router C.
And router A knows this because of the ISIS flooding. So when you set up the original one, originally there was everybody knew that there was 100 megs available on the northern route. Once you reserved bandwidth and set up the LSP, there was a new ISIS link state pack that was flooded saying that now there's only 60 meg available on these given links. So that's how router A knows all this ahead of time and computes the ERO on its own. It doesn't need to, go out and ask people how much bandwidth do you have. It was automatically triggered in ISIS.
Question back here?
Because there's two, we have an administrative wait for how the decision they can be made.
Oh, okay, as far as what routes to take through the tunnel? By default, at least on Junipers, they're randomly distributed. In fact, I'll show you that.
Yeah.
Yeah.
And there's other things you can do too, just because they start and end on the two same routers, you could give these LSPs their own metric, and that way they wouldn't actually be viewed as equal. So all the traffic would take one, for instance. So you can either load balance or play with LSP metrics.
And here's the two LSPs set up. You can see, again, this is our original LSP, again, taking that northerly route. And here's LSP that we named second A to D. And notice here on the record route object, this one is taking 10.0.15.1 to 10.0.13.2, which is router G, to 10.0.31.1 to get to the egress. So it's taking that southerly route. And if I pull back, there we go. Again, this is the same database entry we saw a while ago. Notice, of course, we've still just got 60 meg of reservable bandwidth at router C. If I do the same thing and look at router G, you'll see here, of course, we reserved 70 meg, so now there's 30 meg of reservable bandwidth left on the interface. Notice up where it says local, that's interface 10.0.31.2, which is the interface facing router G. And so we've only got 30 meg of reservable bandwidth left after reserving that 70 meg pipe. Going back to the question about how the routes were assigned, I can do a show route protocol BGP, and you can see that both of these, for each route entry, these 134 routes, again, that we're pumping into the network via BGP, it's showing both of these LSPs as possible hops to those routes. And we've sort of randomly chosen over here which hop we're going to take. The greater than sign here simply shows which route is actually being used. Just scrolling through a few of these, you can see that and it's not round robin, it is random. You can see that these routes.
Why don't you trace right to like a bogus address?
Sure.
One of those.
Let's see. There's a 16.2. Yeah. Let's see if I can. Oh, and before I do that, you can also do just a briefer display. And right here, you can see in this particular case, the randomness is.
So that's the number of routes that are nailed.
Yeah,
that are
the routes that are actually using those two paths.
Resolving through that LSP.
And it is interesting that the second LSP, which is the 70 meg, the 70 meg LSP has 18 routes assigned to it, whereas the 40 meg LSP has 8 routes.
But there's no association. Oh, in our code, there's no association by default.
Yeah.
If we had 1,000 LSPs, you'd see more of a 50-50 distribution. We only have 1,000 routes. We only have 24 routes that router X is pumping into router D.
Okay, this particular trace route, you can see that if I trace to 134.112.11, it's taking that southerly LSP. And I'm going to look back here and just find a different one. Oh, let's say there's 105. And this is a bogus route, by the way, so it'll time out when it gets to the end. But you can see that this particular route traces through that northerly LSP. And it just times out because there's no actual destination there.
Is that it? How are we doing on time here? Okay, we got 15 minutes to the break. So link colors, I think I've mentioned them already. It's just the capability to color links in various places in your network, and this is also carried in the ISIS updates and OSPF updates. And what you can do is at the head end, you can tell the LSP that I want to include links of this color or exclude links of this other color. So it gives you some administrative control over where links go through your network. Or, sorry, LSPs go through your network. So here, what Jeff's doing is he's going around. Initially, our vanilla config didn't have any colors on the links at all. So when he showed you some of the contents of the link state database, you noticed that there was the TLV that carried the information about link coloring, and it always had none. So Jeff's going around quickly coloring these specific links as bronze, and what we're going to do is set up the third LSP to exclude bronze and be 20 meg. So without the exclude bronze, LSP3 should be able to build across the northern route because there's 60 meg available, and because it's the shortest cost from an IGP metric perspective across through your network. But because we've given it the extra constraint that it has to exclude bronze, it won't be allowed to use the link between router B and router C, even though it has enough bandwidth. It has the wrong color, so it won't use it.
Yeah, here's an example on router G of what sort of configuration goes in there. We set up an administrative group. We've defined two groups, one named gold, one named bronze. And in this particular configuration, we've assigned interface FXP0 and FXP2 to administrative group bronze. So basically, we've colored those two links bronze, which is, again, router G. If you look up there, you can see the two bronze links. Going back to router A, let's see. We're going to load this up. And now you can see we've got three LSPs. The two we had before, again, we've got a 40 meg and a 70 meg LSP. Now we've added a third LSP named third A to D. And pretty intuitive names. We've had requested...
Those are my names, by the way. I came up with those.
Yeah, we've requested a bandwidth of 20 meg, a reservation of 20 meg. But the other constraint we've added is this. Under administrative group, we've said exclude bronze. Don't take any bronze links. So if we now look, here's A to D. Nothing interesting there. It's the same one we saw before. Again, second A to D, same LSP we had before. But here's third A to D. And on the record route, let me just scroll this over a little bit. On the record route, you can see that this thing has taken pin 0, 16, 2 to router B, pin 0, 0, 2 down to router E, because it has to avoid that bronze link, pin 0, 2, 1 back up, and then pin 0, 24, 2. And again, remember, going back to what we saw earlier with the traffic engineering database, we had 60 meg of reservable bandwidth at router C. So if that constraint to avoid the bronze link was not there, this LSP would have just taken the same path as LSP1 has taken. And might be worth showing that again.
Yeah, because we'll see the difference in bandwidth now.
Yeah. Let's see, if my memory serves me right. Let's see, 0, 0. Yeah. So we've reserved 40 meg and another 20 meg, so now we have 40 meg left of reservable bandwidth in here.
Can you show the LSP or link state entry for one of the colored, like router G, for instance?
Sure.
so we can see colors being passed around.
Let's see. Did you want the TED, or the?
The ISIS database would be fine.
Okay, here's the TED, and, let's see, get the naming right here. Oops, yeah, sorry.
So the link 10031. Did we pass it? Yeah, we probably scrolled past it. I think it was the first one.
Ah, there we go.
Yeah. No, that's not it. What router did you do? 24?
Did I do D? I thought I did G.
You did C. Or D, one of the two.
I did C.
D should show it as well.
What, D or G?
G, please.
There we go.
So we're looking for 10031 link. So not that one.
There it is.
There it is. So now you can see that the administrative group is now bronze. Yes.
What's the restriction on single affinity group specified LSP, say, include one, exclude one, or actually more complex,
You,
and say, exclude bronze, silver, include gold or platinum?
yeah, you can do both.
So you actually have a relatively complex.
Yeah.
structure.
Yeah, it can
Yeah.
be much more complex than what we're showing here.
Yeah. Yes.
And what circumstances are you getting this reaction?
Well, you might determine that, when you're first laying down your LSPs, some may be carrying more sensitive or more important traffic than others. So under failure scenario, first you want those to be rerouted first, and you want them to come up first and not be preempted by lesser important LSPs. Maybe just because of the nature of the traffic they're carrying is one application. By default, we're very conservative with it because as much as possible, we want to try and not fluctuate state as much as possible in your network, right? So the default settings on our LSPs won't allow preemption. Because you got to be careful with that tool, because if you make things too preemptible, you could start getting, a lot of flapping state in your network depending on the type of failure that occurs.
Last little part here, again, going back and just looking at these BGP routes now, you can see that all three LSPs are shown as possible paths for each BGP route. And again, just scrolling through, you can see that they've been chosen somewhat randomly, which you can also do by doing, and you can see the random assignment here of routes. That's it.
Yep. Preemption. So there's really two variables to track with preemption. There's what they call a setup and a hold. So the setup priority is tracking how much authority I have in setting up my LSP to preempt others, and the hold is how much stickiness an existing LSP has. So for instance, for me to be preempted, the LSP that's preempting me, his setup priority has to be stronger than my hold priority. That's where the comparison is done. Okay? So there's two variables to track there. And by default, ours use the weakest setup priority and the strongest hold priority, and that's why no preemption occurs under default settings on our box. And you want to make sure that, I'm pretty sure iOS is the same way. In Junos, you can't actually have the setup priority, and these setup and hold priorities are per LSP basis when you're configuring them, but in Junos you can't configure an LSP that has a stronger setup priority than it does a hold priority. And you wouldn't want to do that anyways, because then you can get into preemption loops where, you know, I can preempt anybody, but once I'm set up, anybody else can preempt me. So you just, you know, you do this flip-flopping. And this is where, you know, you've got to be careful with how much preemption you turn on in your network, because even if you don't get into this infinite loop of preemption, you still want to be careful that you're not preempting too aggressively, I guess, is what I want to say. Yes?
Are there any good knowledge
I think Wandel is working on some kind of MPLS modeling tool. I'm not that aware of what's out there in the industry. Robert, do you know of anything that is? Yeah. Okay. Yeah, I'm not sure how extensive they are either in their modeling capabilities. That's really, I'm sure you'll hear tomorrow from the panel that's talking about traffic engineering. I think that's one of the things that's lacking in the whole MPLS environment are the tools to configure it, administer it, and troubleshoot it. That's where a lot of things are lacking, but it's still in its infancy pretty much, so hopefully these things will be fleshed out over time. Okay, let me see, I'm doing on time here. Okay, I got just a few minutes. So yeah, on our box it's confusing. 7, which is the highest number, is the weakest priority for either setup or hold. So, you know, it's like the lowest cost is the best. So we also, I say we, but most vendors, I think, give you the option and the capability to optimize existing LSPs. On our box, by default, it's not turned on again because we're pretty conservative in that area. We don't want things fluctuating if they don't have to. But this is useful because you might bring up new bandwidth somewhere in your network, new links, and you don't want to have to go around reconfiguring all your LSPs to go over this link. You can have them re-optimize on their own based on what's in the TED and ISIS database. So this new link has come up, so hey, there's a whole bunch of new bandwidth or more bandwidth between 2 given nodes. Let's use this new link. And you can play with the timers. And again, you want to be careful here too, because you don't want to re-optimize too quickly, because it might just be state changing in your network, and you don't want that to be getting you in like lots of not re-optimization loops, but with all these knobs, you want to be careful that you're not creating too much churn in your network. And I'm attending the panel tomorrow because being on the vendor side, I don't have as much operational on the large scale as some of these guys do, so I don't know what the right number is here. You know, if that's a question that might come up. What is the right number to do with re-optimization? I'm not sure. It has a lot of variables, you know, number of LSPs, size of your network, state and stability of the links in your network. Yes?
So once you bring up ICP across in your link, is the actually delegating information automatically?
Yes, it is.
So just curious, they're disabled by default. That means that once the LSP is set up, no new ICP updates make things like it's like a static number?
No, the TED is dynamic, but the LSP itself won't take advantage of that new information. It won't reroute itself unless it fails. But if it's up and working, it won't. This isn't really rerouting under failure. This is re-optimizing. My current path meets all my constraints just fine. All of a sudden, there's a new path that could do it better, like there's more available bandwidth. Yeah, you could clear it on the head end, just do a clear. Yeah. This just allows you to do it automatically. And again, it has to do with LSPs that you've deemed of a higher priority. If a link, here, let's go back to, do we have a picture of our, so for example, let's say the green LSP was high priority. If the link between B and C were to break, you would definitely want that LSP to be able to reroute. And because it's asking for 40 megs, by default, it won't be able to share any links with the red LSP because preemption doesn't occur. But if you said, if based on your network design, this green one was of a higher priority because it was carrying more sensitive traffic, well, you would want that green one to be able to preempt the red if it had to. So that's a more pertinent application, I think, of where you want to use preemption. You want not only the more important ones to reroute first, but you want them to be able to bump lesser important LSPs. So what would happen is if, the links in the middle broke, the green LSP would bump the red LSP and the LSP just wouldn't come up in this particular topology. In a more real network, maybe the red LSP would have to reroute some other way. So that's another good example of why you want to be able to do preemption. We talked about optimization. Here are the rules in Junos. I'm not sure what the rules are with other software, but just kind of, they're probably somewhat generic and conservative. So you only re-optimize if these conditions are met. And like I said, these are true to Juniper, and they're probably pretty generic in many cases. Because again, you want to be conservative. Let's talk a little bit about load balancing of the LSPs themselves across what may be equal cost or equally valid paths through your network. And again, this is vendor specific. It's not part of the draft, but I'm sure you have various levels of granularity to do this in every vendor's implementation. We'll show you examples of ours, but they're probably not that much different than anybody else's. So by default, we do it randomly, as you've already seen, but you also have the option to do least fill and most fill. Least fill is where you will truly sort of round robin your LSPs between all the equal paths through your network. Most fill is a knob where you'll actually just keep laying LSPs down one path until it no longer meets your constraints. And we have some demos to show how this works. And that takes care of load balancing the LSPs themselves. And then we'll talk a little bit about how you want to load balance traffic through those LSPs and how that's done. So I talked about these examples already. So basically the way this works in Junos for these least fill and most fill options is we track the minimum available bandwidth ratio on any path through the network. And what that is in your link state database, you have the maximum reservable bandwidth, right? And you have the available bandwidth on every link in your network. And so for a given ingress to egress path, you have the minimum ratio of those two numbers. So for every link, you can take the available bandwidth divided by the maximum reservable bandwidth, and it gives you this available bandwidth ratio number. And you can do this for every link in your network, so you can determine which one is the smallest for every given path. So who has the least amount of available bandwidth for you. And the way it works is basically least fill is you lay the LSP down the path that has the biggest number for that ratio. And what it ends up doing is, like I said, it pretty much round robins your LSPs across the 3 or 4 or 5 or 6 possible paths. It'll kind of round robin them that way because you're always looking for the one that has the most available bandwidth left over. Most fill is the opposite. Can't think of any applications off the top of my head why you'd want to do this, but there are, I'm sure, some. This is where you take that same ratio and you take the path that has the smallest minimum available ratio. So what you'll end up doing is you'll keep laying the LSPs down the same path until it no longer meets the constraints of the LSPs trying to go through your network, and then you'll take the next path. All right? An example might explain this better than I just did. So do we have it? Yeah.
Okay, the thing to know about that, the picture shown there is that we changed a few configurations so that now you've got equal cost paths both across the top and across the bottom. We changed the ISIS metrics.
Yeah,
So you can see that, sorry, go ahead.
this used to be 10 and that was 10, so we didn't actually have equal, routes through the network. Now the northern and southern are equal because all the bandwidth available on every link right now is 100 meg. The IGP cost is the same and the router hops are the same. And link colors we haven't colored anything and we're not using them as constraints, so they don't apply here.
And just for the example, you can see here on what we've done here, let's go through all of them. We've set up MPLS now with 12 LSPs. They're all the same in that every one of these 12 LSPs goes to the egress router of router D, 192.168.24.1, and every one of them asks for a bandwidth reservation of 10 meg. So all 12 of these are the same. There's nothing else specified in here at this point. So by default, the BGP routes will be assigned randomly, and you can see that easily enough with just sort of the LSP summary here. You can see that there's sort of a random distribution of routes assigned to these 12 LSPs. And next,
You can show the routing tables. Is that worth it?
Sure. Yeah, you can see that every one of the BGP routes, I won't scroll through everything, but every one of the BGP routes shows all 12 LSPs as possible paths, and then sort of randomly choosing them. Okay, this time, loading a different configuration in. It's the same 12 LSPs, but now we've added the keyword least fill to each one of them. And you'll notice that only the first LSP is actually enabled. All the others right now are disabled. So if I start off by just doing a show LSP, you can see that all 26 routes here are assigned to the single LSP. It's the only one that's up. So what I'm going to do is just for a few of these, I'm going to go through and enable a few LSPs. I'm not going to go through all 12 for this example, but let's see.
Don't forget to disable.
Yeah. There's one, and let's see. Go at the board here.
He's just basically enabling the LSPs one at a time to see where they end up getting load balanced.
Okay, so I've enabled 4 of them, and actually, that's not what I wanted to do. Going through and looking at the LSPs with 4 enabled, the very first one took this northerly path.
Yep.
Through
Across the top here.
16.2, right there. The next one that came up was assigned to the southern path. 10.0.15.1 is the next hop of that one, going through router F. The third one that came up was again assigned to 16.2. And the fourth one that comes up takes that southern path again. The point being here, I could keep going through all 12, and every time I enable one, it'll round robin distribute them across these paths. So it's the only real point there. Okay, I'm loading a different configuration here. This time, again, the same 12 paths, the same 10 meg required on each one, but now we're doing a most fill. And what should happen here, and by the way, going back again, we've got one LSP enabled, everything else is disabled, like before. What should happen now is a single path will be used for every one of these LSPs until all of the reservable bandwidth is used up. So if I begin by just doing a show LSP extensive, there's only the one LSP there, and it's taking that northerly path through 10.0.16.2. Again, that's the one going up through router B, router C, and router D. And bear with me with these, going through these commands. It takes a second, but what I'm going to do is start enabling paths. Anything entertaining to say while I'm doing this?
I should have brought some Jekyll and Hyde or something. This one we actually have to go through more of them because we want to show you where at some point we exhaust the bandwidth on the northern route here. So at some point we no longer actually have equal cost paths because one of them no longer meets the constraint of the LSP. So therefore it'll only have one option, and that's the southern route. Whoops.
Okay, I've enabled 8 of them so far, and what we can do is just scrolling through these, you can look and tell every one of them is taking this northerly path with the next hop of 10.0.16.2 with the ones that I've got so far. And I believe I've enabled 8 so far, all of which are asking for 10 meg of bandwidth. So if I also look at my traffic engineering database, let's look at router C. You can see that at this point, with those 8 enabled, I've got 20 meg of reservable bandwidth left. So now I'm going to enable my last 2, or not, I'm sorry, not the last 2. And looking back again, oh, it hasn't taken effect yet. It takes a second to signal through. There it goes. You can see now I've got 10 LSPs enabled, and I've used up all of my reservable bandwidth at router C on that link facing towards the egress router. So the next 2 LSPs that I enable have no bandwidth left to go across that link. So, or across that path, sorry. And one more. Just scrolling through these, here's LSP1, LSP2, LSP3, LSP4, and as I said, they're all following that northerly path until we get down to LSP, notice LSP10 here, still on the northerly path. LSP11 now goes on the southern path, and so does LSP12, based on available bandwidth.
So just to show you that there's some variations in how you can load balance LSPs across paths, and iOS has their variations as well. So we talked about load balancing LSPs across your network. Then the next level of granularity is how do you load balance traffic through those LSPs? And again, this is vendor specific, but I think, you know, the capabilities are similar and generic across the vendors. If you're running our older forwarding engine, the Internet Processor 1, you pick a next hop based on a per prefix basis. So in other words, every route in the routing table, whether it's /24s or /16s, will be assigned to a next hop. So all traffic going through that address space goes to that one next hop and that one next hop only. With the Internet Processor 2, the second generation of our forwarding engine, it's more granular than that. It's per flow, you can call it. So, you know, we look at the source and destination IP header fields, and that's how we pick our next hop. So a given TCP flow will follow one LSP. The next TCP flow, for instance, will follow the next LSP, and so on and so forth. And I believe Ceph in iOS does a very similar thing. So this is a diagram without LSPs configured. You have traffic being distributed across equal cost IGP paths in some manner. You know, this one prefix is tied to the router B as the next hop. The next prefix 10.0.15/30 is tied to router F as the next hop.
And you can kind of see that if I just delete MPLS completely out of my config, obviously all of the LSPs go away. And then do all of my BGP routes that were there are now just load balancing over, there's no LSPs left. They're randomly load balancing over the IGP path.
Over the physical next hops, basically. So
Yeah.
you're pointing at an IGP next hop, not an LSP. So this slide just shows that you have the exact same behavior, but now your physical next hop isn't really an IGP route per se, it's an LSP that is the next hop. Did you want to?
Got another.
That was it? We kind of showed it with the routes on the last slide. Is that what the?
Yeah, this one, the example here is more or less what you've already seen earlier. Let's see, I just brought all the 12 LSPs back up.
So this traffic load balancing is, you know, kind of outside of the standards of MPLS. It's more vendor specific.
Yeah. With all the thrashing, it takes a second for them to come back. There they are. You can sort of see, again, I've already pointed this out, but all the routes with 12 LSPs here, they're randomly balanced across those paths.
Okay. So we'll get into a few more bells and whistles with MPLS. One important topic is traffic protection. We already touched on it a bit, but there's various levels of protection you can use within your network when doing MPLS traffic engineering. And some of them are, well, by default, if you only have one MPLS LSP configured across your network, and you don't have any explicit backup mechanisms for that, it will just reroute itself should something fail. So do we have, how far do I have to go down now? Kind of far. Okay. So if you remember the picture we've been using for our lab, and the green LSP that goes across the north, if one of its links should fail, once router A realizes that, it will just try and find another path for that LSP through the network. But that takes a certain amount of finite time because first, where the failure occurred, the node that's attached, for instance, to that link, there's time in how long it detects that the link is down, and then it must signal back through both RSVP and an ISIS update flooding or OSPF update flooding back to the head end. So the head end doesn't know that that link is down and continues forwarding traffic down the LSP until it gets this notification. And then even once it's got this notification, then it has to start rerouting that LSP. So it has to do a CSPF computation to find a new path. And then once it's done that, it's basically got this new ERO, right? And it has to go re-signal the new or the same LSP over the new path. So there's a certain amount of time involved with that kind of reconvergence scenario. So you can do certain things with MPLS to improve that reconvergence. One of them is building secondary LSPs or paths. So you have your primary LSP that's set up and being used, and you have this secondary LSP waiting to be used should the primary fail. And each one of these features just kind of tries to improve on the time involved in reconverging and on the time you're sending traffic down an LSP, and it's just going to drop somewhere in the bit bucket. Okay, and we'll go into some of the details of each one of them. So I talked about the first one where it just reroutes on its own, and there's no secondary, and that's what this slide kind of talks about. Here's a retry timer where once you've failed, here's where you're continuously trying to find a new path for that LSP. So you can play with the variables as to how often you retry to lay that LSP down across your network and how often you do this computation. Because if a link fails in such a manner that there is no path across your network, you may not want CSPF to continually try to reconverge this LSP. So you can play with numbers that play with how often you do this computation when you're trying to reroute it, and you can give it a ceiling for how many times ultimately it can retry this. And if it's tried it 100 times, chances are there's pretty hard state down in your network somewhere in your network, and it should probably stay down and stop recomputing. It's probably not going to be successful. So you can play with these. This is kind of Junos specific, but there's probably variables like this on other vendors' boxes as well. And this applies to the primary LSP. But you can also configure, excuse me, I'm starting to lose my voice here. You can also configure secondary LSPs to help with how quickly you start rerouting traffic under failure scenarios. So this is the case where, one example, I think I already touched on, where you can have the secondary LSP tied to the primary so that as soon as the head-end router finds out that some link along the primary path has failed, it can now switch traffic over to the secondary LSP. And there's even two modes within this. You can have the path for the secondary LSP specified so the head-end router knows what it should be, but it isn't signaled yet, so the state in the network hasn't been set up. It still improves on the worst case scenario because you don't have to do the CSPF calculation, it's already been done, but you still have to go out and signal this secondary LSP. On top of that, you can put that secondary LSP in standby mode, where you not only have you specified the path that the secondary LSP should take, but it's there and the RSVP state is reserved throughout the network. So in this case, if as soon as the head-end router finds out that a link has failed along the primary, it can literally switch the traffic over immediately to the secondary LSP because it's up and live in the network. So you can see how each one of these kind of features builds on each other to reduce the amount of time where traffic may not be properly routed through your network or maybe dropping into a bit bucket somewhere.
How do you synchronize the running of the MPLS or HTTP?
Well, there, if you have the standby mode for your secondary LSP, it has to be signaled, and it's signaled just like any other LSP would be signaled through the network, and the same CSPF algorithm is run on the link state database to choose what that path should be. And you can add constraints to it as well that are maybe different than the primary. You have quite a bit of flexibility there as to what you can do.
I'm just thinking of a link that goes down between two routers and goes and router protocol has to run MPLS and also.
Yeah, so your code has to know that this particular LSP is actually a secondary trying to protect the primary. So what it'll do is it'll, in our implementation anyways, and probably most others, it'll try to avoid as much as possible the path that the primary takes. So that's an extra thing, it has an extra check it has to be aware of when it's calculating the ERO for the secondary path. I believe we have some demos coming up, we'll show you what that looks like. Yeah. So again, just in case it wasn't clear, the only distinction between not having standby on and having it on is in one, when you don't have it turned on, you know the ERO, but you haven't reserved state anywhere in the network, so you have to signal. So there's an extra amount of time in doing that. With standby on, the secondary's there and it's available to use as soon as you need to cut over.
So the bandwidth that is served by the MPLS
Is what?
is unused.
Yes, good point. Today, anyways. Maybe in the future you can actually use some of that bandwidth. Today, in our implementation, it's not being used. So here's an example where we'll build the primary that does this kind of weird M shape across the top, and then we'll protect it with a secondary. And you'll notice in the slide that we haven't specified any bandwidth for the secondary because we've determined that, you know, this is really for only failure scenarios, so we don't really care if there's 20 megs on RSVP available or not. You could just as well specify 20 meg for the secondary. You got to be careful though that there is an alternate path that can meet those constraints, otherwise you won't have a secondary to fail back to.
And we've got an example of that a little bit later. First thing to show, I've already loaded the configuration in. Under MPLS, what we've got, again, our original friend there, the LSP A to D, again going to the same egress router. We've defined a primary path, named best path, that should reserve 20 meg of bandwidth, and our constraint there, besides the 20 meg of bandwidth, is that it has to exclude bronze links, can't take bronze links. We've also got a secondary path that we've named standby path that's simply in standby. It's not much more that's interesting about that other than we've specified a standby path. And if we do if we look at our LSPs, here's the LSP, and you can see that this is the primary, and that on the record route, again, let me scroll this over just a little bit here. The record route, this thing is taken 10.0.16.2, 10.0.02, 10.0.21, and 10.0.24.2, which is that M-shaped path across the top that Chris is showing you there. But below it is the standby path here. And you can see that the standby is up, it's ready to go, and the particular path it's taking is across the bottom, 10.0.15.1, 10.0.13.2, and then finally to 10.0.31.1. So just what's being shown on the slide there.
So this will protect against any intermediate link or node failing on the primary. You'll be able to switch over to the secondary. It doesn't protect you against the following failures: the ingress router failing or the egress router failing, because that's the endpoints of your tunnel. So if either one of those two routers fail, your LSP is down and you can't really do much about it. We've talked about secondaries. There's also the capability in RSVP to define your reservations in such a way that they share bandwidth on links. And this is what this adaptive mode is speaking about. So actually this example isn't good. I think the next one. What it does is when we set up the secondary in the last example, it was actually reserved, well, we didn't specify any bandwidth, but had we specified 20 megs for the secondary, it would have actually have reserved 20 megs along those links, even though it wasn't being used, preventing that from being used from some other LSP. And you get into cases where you can get double counting because we said that the secondary tries to avoid the primary, but if there are situations where it can't, without turning this adaptive mode on, both the primary and the secondary will nail up bandwidth on the common link. So if they were both had a constraint of 20 megs, 40 megs would be reserved on that common link. You can turn on this adaptive feature of RSVP, and therefore you don't get this double counting on that link. Only the 20 megs will be reserved. And here's a slide that kind of shows how that works. So these two sessions, 1 and 2, have adaptive turned on, and therefore they're, in RSVP terminology, they're what they call shared explicit LSPs. So they share the reservation of that middle link. So instead of double counting on that link, you only count the bandwidth once. The default mode in our software is what's called fixed filter, so that they're each treated separately, and therefore they each reserve their own bandwidth on that link. So we're going to bring up an example here where we actually asked for 20 megs, and this time we also forced the secondary to share a link with the primary by having it exclude gold. It's kind of a busy slide, but...
Okay, you can see the configuration here. Again, HD, 20 meg, and we're excluding bronze. Now, on our secondary path, we're also specifying that that secondary path must reserve 20 meg of bandwidth. And it's excluding gold. And here, in this particular example, as Chris said, we're really using our administrative groups more than anything else to force these two LSPs to use the same path between router E and router C, more for the example of showing what happens when two LSPs share the same path.
So first we'll commit it without the adaptive mode, and we'll see what the bandwidth reservations look like, and then we'll turn adaptive on. And by the way, this adaptive mode I keep talking about is an RSVP thing. It's not Juniper specific.
Yeah, and if you look here with the default before we change anything else, just doing kind of a summary on the RSVP sessions, you can see that the style of these reservations is fixed filter, the FF style. And let's see, if we now do we're going to look at
Siri.
let's see, we want to do E actually.
Sure.
Okay, what's happening here, we're looking at the TED database, traffic engineering database for router E. And you can see this link going from router E to router C has 60 meg of reservable bandwidth. So what happened there was our primary LSP reserved 20 meg of bandwidth, and then the secondary LSP reserved another 20 meg. So now we only have 60 meg of reservable bandwidth left. So the next thing I'm going to do here is change the style of that LSP to adaptive. And let's see, just doing a quick. Pretty much everything looks the same, except now I've got that adaptive keyword in there. And what we should see now. Well, the secondary path hasn't renegotiated yet to come back up, but you can see that we've got this SE style now. And let me do this a couple more times, waiting for the second. There's the secondary path back up. So we've got an SE style on both of those. So it changed from fixed filter to shared explicit. And if I now go back and look at that same traffic engineering database, you can see that now the reservable bandwidth, the bandwidth that's left after a reservation, is 80 meg. So the primary and secondary path only reserved that 20 meg of bandwidth once, and they're sharing that bandwidth instead of each making their own reservation.
Okay. Yet another capability to protect your LSPs is this fast reroute capability. And I think they're actually right now in this drafts and standards bodies that are working on trying to formalize, protection mechanisms for LSPs. The concept of this one is kind of generic. The way this is done in Juniper is obviously specific to our implementation, but the idea is pretty generic. And basically what this is doing is it's protecting every LSP by rerouting around every downstream link and node. So what it does is it builds these detour LSPs, if you will, around every downstream link and node. So should any one of those fail, you immediately take this detour path. So even in the previous example where we had this secondary and standby, router A won't use the secondary until it knows that the link between B and C has failed. And that's a finite amount of time, right? Either through ISIS or RSVP updates. What fast reroute will let you do is B knows that that link has gone down pretty quickly if it's, for instance, a SONET link. And what it will do, it will use its detour LSP immediately. So yet again, you have traffic taking a working path in a much smaller amount of time under a failure scenario. So I think I have a slide that shows this. Our implementation is Juniper specific. It's something that's signaled in RSVP to tell the other routers that this is an LSP that needs to be protected with our fast reroute mechanism. So when you're signaling the original LSP, you're telling the intermediate routers, you need to be building detour LSPs to protect your downstream link and neighbor. All right, so that's how this is all being set up automatically. So here's an example. You have this primary LSP through A, B, C, D, and E. You enable fast reroute on the ingress only, and automatically the intermediate routers will start building detour LSPs around their downstream links and nodes. If they can, you may have topology scenarios where not every link, downstream link and node could be protected. And we don't have an example, but I'll go up and I'll show you one of those possibilities. But in this particular example, you have enough physical topology that you can actually protect every downstream link and node. So what will happen is if the link between B and C fails, B automatically reroutes around the failure using its already existing and up detour LSP. Now in our implementation, this is just an interim solution. Ultimately, we still want the head end to find a brand new path through the network. So until the head end does that, traffic will go from A to B and then go into the blue detour LSP. But as I said, it's a short-term solution because ultimately you want A, once it's found out that that link has gone down through ISIS or RSVP, to find a new path through the network. And once it has done that, we'll switch over from this detour path to the new primary LSP. And again, the goal here is just to shrink the time between when the failure happens and when traffic takes a working path.
How is that level of complexity any better than just falling back to the IP?
Well, that brings up another good point. And it's kind of implementation vendor specific, that's why I haven't brought it up yet, but the reality is on our router, for example, even if the LSP were to fall apart and die and never be rerouted, once we know it's not usable as a next hop in our routing table, we'll follow the regular IGP paths at that point, right? But if we think the LSP is up when it actually isn't, we'll start putting packets into the LSP that will actually, or may drop on the floor somewhere. But once we know it's not there, yeah, we'll fall back to the regular IGP routing. But that's kind of vendor specific. It's not necessarily doesn't necessarily work that way in everybody's implementation. Yes.
If you have a situation where you have a line of routers, basically, where each router has two, that are kind of mesh like this, will pass-through route go back the way it came to go around?
No. It may try. It may think it can do that. So the router, let's think of an example here. Well, let's say this link here wasn't there, right? Router D, to protect this link, may build an ERO for its detour path that goes around like this, but when it actually tries to signal it, the record route object of RSVP, if it truly is a loop, will detect that loop, and you basically won't have this detour path. This is what I was saying where you might not always be able to protect every link and node. It depends on your topology. Yeah, Paul? Yeah. So it could go back on the LSP path? Because I've tested this and I don't know. Yeah, Paul works in our TAC. Yeah, I've seen scenarios where you're right. We tried to go back through the ingress, and it wouldn't allow it to happen. But I'm pretty sure I've also seen scenarios in our code where it just tried to backtrack on itself and didn't hit the ingress and still wouldn't build. But anyhow, again, this is kind of Juniper specific, so I don't want to get too much into detail. Just that it's generic enough in the sense that you know, other vendors, and they're also talking about these types of protection mechanisms in the standards body. I just wanted to demonstrate it. I know for a fact iOS has a protection mechanism that we don't. The downside of protecting LSPs this way is it's a per LSP protection mechanism. So you're building all this other state for every single LSP that you're protecting with our fast reroute. So that's creating more RSVP state to track in your network, right? iOS has a feature where they'll protect a link by building one detour LSP around the link, and any LSP going across that link will be switched over to this protect LSP. The upshot of that is that you're only keeping state for this one detour LSP, and you can protect a whole lot of LSPs. The downside is it's only protecting that link. I mean, you could deploy to multiple key links throughout your network, so maybe you can come out with some kind of protection topology where it completely satisfies everything. But there's pros and cons to both features. And I guess, I'm sure as time goes by, most of the vendors will have pretty much all the, you know, bells and whistles. You'll have a choice of which ones to do. Yeah. Deploy the protection mechanisms? Actually, Paul would know more about that than me. Paul, is fast reroute being used a lot by our customers, do you know, yet? Because there's all sorts of ways to provide this protection. We talked about the secondaries. You could just have, you know, multiple LSPs. There's also the fact that our box will just start forwarding with the IPv4 routing table once the node knows the LSP is down. But it's a feature available to you if there's some really critical traffic. And you know, it's even the fast reroute LSPs, I'll reiterate, in our solution, it's a temporary thing. It's a temporary state. The head end is still going to find a new LSP path through the network. It's just to bridge the gap between when the link fails and when the head end finds out about it, basically. Okay? This is LSP. This is just a listing, you know, some of the events that might happen in your network to cause an LSP to reroute. We talked about, let's see here, where'd my pointer go? We talked about optimization, which on our box is off by default, so that might cause a reroute. We talked about failures. We talked a little bit about preemption. Whoops. So another LSP comes along that has a better setup priority than my hold priority. It'll preempt me, and therefore I'll have to reroute. And the last point here where it's a make before break, again, that's kind of vendor specific, but somewhat generic, because I'm sure everybody else has this mentality too, or allows you to configure it this way, where if I'm forced to reroute, let's say for re-optimization, I'll build the new LSP, make sure it's up before I actually switch traffic over or stop forwarding traffic over the old LSP. If I can make before break, I will. You can't always do that, but I think most vendors give you that kind of option. Yes? For each detour LSP? Yeah. But you can assign bandwidth. I believe so. In our code, we'll let you assign. By default, they don't. Okay, so but I think you can assign bandwidth to detours. Again, this is vendor specific, but by default, they won't. They won't inherit the primary bandwidth. But I'm pretty sure I've seen a knob where I've done, you know, or maybe I'm thinking of secondary. Yeah, sorry, I'm confusing it with secondaries. So by default, fast reroute in our box doesn't, because it's such a kind of temporary solution, you shouldn't care. I shouldn't say you shouldn't care. You probably don't care about reserving the bandwidth, because like I said, ultimately you'll build a whole new path through your network. It's again, just to bridge the number of seconds of that gap, right? So if you put a constraint on it to reserve bandwidth, you may be eliminating the possibility of building these detour paths by giving them, you know, hard constraints, when really they're only going to be used for a very short period of time. But if it's a feature you want to see, I don't know, send, you know, Paul's like, no, okay. Don't send us any requests. Just kidding. That's, yeah, and for a very short period of time. But because I work for the vendor, I'm not allowed to say you shouldn't, or it's stupid to want that, because you may find an application where it's useful. I don't know. Route resolution, we talked about this a little bit. The way this is done in Juniper, again, is specific to our code, but it's just, what it's pointing out generically is that in most vendors' implementations, you'll have the flexibility to be able to bind certain routes to LSPs and not others. For instance, in ours, by default, only BGP routes will resolve to LSPs. The idea behind that being you probably want to traffic engineer your transit traffic, so traffic coming in and leaving your AS. So that traffic is usually forwarded based on a BGP route. So by default, we only bind BGP routes to LSPs. But we do have knobs to change that where you can bind every route, and we'll get into some examples about that. But the point I think we're trying to make here is you have some flexibility as to which routes you actually bind to these LSPs and which routes just follow the regular IGP path. So here's an example of this 134, 112 BGP route coming in. It's sent over via iBGP to router A. So you've seen all these routes before in some of the other examples. And in this case, the way it works in Juniper is if the BGP next hop is the endpoint of an LSP, you can use that LSP for that BGP destination. And we'll show you a knob where if, for instance, this is just your core, and the iBGP router that sent you this is further down in your network hierarchy, so the LSP doesn't actually go all the way to that BGP speaker in your network, you can turn on a knob that'll allow you to use the LSP even if, you know, the BGP next hop is removed from the endpoint of the LSP.
This first example is really just what you've seen before. This is kind of going back to, we turned CSPF off and we specified a strict route that is following the path in green shown over there in Chris's slide. And if I do a trace to one of the BGP routes, the only point really there is simply that our trace route, or our path is taking the LSP. So it's somewhat of a trivial example there, but it's a starting point for the following example.
In this example, what we'll do is we'll have the BGP next hop variable be different than the endpoint of the tunnel. So in our case, because we're limited to this infrastructure here, the endpoint is just going to be the regular eBGP next hop address is .2 address, so we're not doing next hop self. But, you know, a more interesting example would be where the BGP speaker that injected this route into your network is like 3 or 4 hops removed, and this is your core. And in our case, by default, you won't, that BGP route, because it's next hop, isn't the endpoint, the 24.1 of this tunnel. You won't actually use the LSP to resolve the BGP next hop. But we're about to show you how you get the granularity to turn on a knob to allow that to happen as well. So the next hop in this case is 172.16.4.2. It's not the endpoint of the tunnel, and therefore A won't use the tunnel to resolve that BGP next hop by default until we turn on a certain knob.
Right. What I did here is just go up to router D and basically change the configuration to take out that next hop stealth portion of the config. So I'm back at router A now, and if I do the same trace route that I did before, you can see that now it's not taking the LSP at all. It's simply a regular old vanilla IP trace.
It's going across the top path here.
Yeah.
And if you show the route, you'll see that the next hop just simply resolves to this .16.2 address, the IGP route. So it no longer points down an LSP. But in a sec, we'll turn on a knob that will allow everything. Again, it's just specific to BGP routes in our implementation right now, but it'll allow everything downstream. Any BGP route that has a next hop of the tail end of the LSP or something downstream from it will be able to use the LSP to get there. Do we have a demo for that, right? No?
Yeah, coming up.
Oh, I had a slide on what the knob is. In our implementation, it's called traffic engineering shortcuts. So again, if the BGP next hop lives downstream from the tail end of your LSP, by turning this knob on, you're enabling the use of the LSP to get to those BGP updates.
Which is done fairly simple here. In this particular case, it goes under ISIS, and I'm going to say traffic engineering shortcuts. And then, let's see, if I come back to that, if I do a trace again, once again after, okay, looks like we need to pause again.
5 minutes?
5 minutes, okay.
Okay, we got to change tape.
We've got to do a tape change pause again here in a second. But again, after I enabled traffic engineering shortcuts at ISIS, for my ISIS configuration, again, I'm taking the LSP to get to this BGP route. And I can also do there it is, do a detailed look at that. And you can see that we're again using the label switch path on this route for 134, 112.
And this is only for, again, BGP prefixes just now. We'll get to another example that opens it up for everything. But this is interesting because you may only want to do traffic engineering across your core, but the BGP routes came into your network somewhere else within a regional WAN, and so their next hops might not actually line up with the endpoints of the tunnels you've built across your core. So you can turn this on to use those tunnels for transit traffic even though the BGP next hops don't align perfectly with the tunnels. And until the next knob we're going to talk about, this is all just for BGP prefixes, in other words, transit traffic through your AS. Not yet. Not yet. At least not in Junos. It's coming. Because that's basically source routing, and we don't have that just yet.
You've got this slide, another slide, example.
Okay. So what we're going to show here is the default behavior I just talked about. You can see that the transit traffic is actually going through the LSP because it's based on a BGP learned route, but you may have this web server farm inside your network somewhere that's not a BGP route from your perspective, it's an IGP route. It's an ISIS destination. And so in our default behavior, that web traffic won't actually go down the tunnel, even though the web server farm is hanging off the tail end of that tunnel. So you can turn on yet another knob called Traffic Engineering BGP IGP. So basically you're turning on traffic engineering for both BGP and IGP. And now all traffic should go down that tunnel.
And what I did previously while Chris was talking was, again, go to router D, and I just loaded a config that kind of fakes a route to what would look like the server farm up there. So before doing anything else, if I do a trace, let's see, what's the address? 10.57.16.1. You can see that I'm using the IGP path. I can then go in and enable traffic engineering over both BGP and IGP.
And the slide indicates all traffic. More precisely, it's all traffic going to destinations downstream of the LSP. So if you were pinging, for instance, router G's loopback, it wouldn't go down the LSP.
Yeah.
But anything downstream of the LSP tail end will use the LSP in this case.
Right. And so
yeah. It's been around for a while as far as I know. Paul? No? 4.0. Oh, okay. I thought it... Yeah, I'm more familiar with the ISIS capabilities, so 3.4 or 4.0.
So after enabling this, if I run that same traceroute command again, you can see that now this is the destination internal to the IGP domain and known by ISIS, and yet I can still take the LSP to reach that destination.
So last slide, being able to hide the MPLS hops in your network. Now that you have this TTL field that's separate than the IP TTL field, you can do some interesting things. By default, when an IP packet comes into the head end of an LSP, the IP TTL field, well, first it's decremented when it first comes into the router, but then what's left over is copied into the TTL field of the MPLS packet, and that's decremented as usual through the MPLS hops, and then at the egress router or the router that pops the last label, it will copy that MPLS TTL field back into the IP TTL field, in which case, which like you've been seeing all day, we see all the hops, the MPLS hops and the IP hops. Now you can turn this off, and most of the vendor implementations I'm aware of have a knob, even though they might work a little differently, that essentially do this. In our case, you'll set no decrement TTL on a per LSP basis, and what it does is on the ingress router, and you only do this on the ingress router, by the way, what it'll do is instead of copying the incoming IP TTL into the MPLS TTL, it'll just ignore the IP TTL and set it to the MPLS TTL to 255, the highest possible number, given the number of bits you can play with. And the intermediate transit LSRs will decrement that TTL as they usually do, but then on the router that pops the label, it will not copy as it used to do, the TTL back into the IP header. So what essentially happens is the LSP becomes transparent to the IP TTL field. So a packet will come in with IP TTL 9, let's say, get decremented to 8, and then it's encapsulated into an MPLS packet with a TTL field of 255 that gets decremented, and then finally that's popped, and you're left still with that 8. So if you do a trace route, you'll miss all the transit routers in your LSP. So it's giving you the ability to hide the MPLS hops in your network. I think there are efforts going on to come up with some kind of standardized way of doing this. I know initially our implementation in iOS didn't interoperate. I think recently we've added some knob where we can get the two to interoperate. Yeah. 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 Robert can correct me if I'm wrong. As far as I know, the way iOS does it is you configure like no propagate TTL, different name for the knob. They also start off with a 255 TTL, but then at every node, the node makes a decision, okay, should I, I decrement it, but then when I'm popping the last label, I think they have some kind of decision tree where they'll go, based on the value of the label, should I copy it into the IP or should I ignore it and make it transparent? Is that essentially how it works?
From the your MPLS back TTL is lower than your IP, then you copy. Higher than you take the IP and don't worry.
Exactly. So you make this decision regardless, right?
Yes.
Yeah. Okay. So it's not something that's signaled through RSVP, right? No, exactly.
It's per router for even tenant right now.
Yeah. So our no decrement TTL knob is actually something that is signaled in RSVP to the rest of our Juniper routers that a Cisco router wouldn't understand. But we also, as Paul was saying, we have this new knob that's called no propagate TTL that allows us to interoperate with Cisco. So, the way various vendors do this right now is somewhat proprietary, but I think there are efforts going on in the IETF to come up with some kind of, I don't know if it's going to be a standard or just a recommendation or draft, and even if they don't, we know that we have to interoperate, so eventually we both tweak our knobs to work together. And that's it.
Well, actually, there's a...
Oh, we got an example, sorry.
A small example here, just to show what, just to illustrate what Chris was talking about. I'm just doing a trace route to one of my BGP routes, and just to make it interesting, or try to make it as close as I can to a trace route that has entered before the LSP start, or the LSP starts, I'm sourcing it from the loopback address of router A. And obviously, you've seen that before. It's simply showing that here, when I do a trace route, all of my LSP hops show up. All of the LSRs are in there. So if I then go in and say set protocol, MPLS, we're going to do it on this label. And I've got the no decrement TTL. I'm going to commit that. And I'm going to pause for a second to give RSVP a chance to signal that through the network. And let's see if it's had enough time. Yeah. There you can see now when I do a trace, sourced from the loopback of router A, the LSP doesn't show up at all in that trace. The first hop that shows up is 10.0.24.2, which should be it's the interface of the egress router. So essentially, someone from outside trace routing through your network does not see any of the details of the MPLS configuration within it. They simply see the entire MPLS cloud, if you will, as being a single hop.
But in my experience, customers complain more about the delay numbers they get when they do trace routes than the hops. So this doesn't hide the trace route delay numbers. It just hides the hops.
Is there any way internally to still see the LSP hop?
Not with trace route, but you can with the record route objects of the LSP and RSVP sessions.
Yeah, pretty much, just look at the LSP and the record route.
So that'll tell you where the LSP is going, and if you want to know where the traffic is actually going, you can just look at the routes. Like if you do a show route for that, wherever you were tracing to, and you'll see that it resolves through an LSP.
Yeah.
If it wasn't, that next hop would be just another route or IGP route, basically. Okay. That's all I have in slide material and demos. Any questions? We have 10 minutes left. Yeah.
Quick question about the LSP, I thought that was not there,
So you mean based on like other metrics like delay and congestion on the link? Not currently. Yeah, at that point you could manually tweak, the variables you can play with, like the bandwidth of the link. You could, reduce it and then clear your LSP, and it'll be built over a different path. But that's kind of manual. It's not. I didn't catch the last part. Sorry, I didn't quite hear it. Okay, yeah. Delay and congestion doesn't enter the picture yet. One point I wanted to mention, I forgot to, and somebody made me think about it during the break, was all this bandwidth we're talking about so far is with respect to the LSP itself. In other words, the LSP is reserved 100 megs of RSVP bandwidth on an interface, or let's say we'll go back because our links are 100 meg, let's say we say 50. There's nothing going on within that LSP to actually police the traffic going through it. Is that clear? So if I build an LSP from router A to router D with 50 megs, that 50 meg bandwidth is really only an abstraction for the LSP passing itself. It has nothing to do with the traffic going through the LSP. So you could build this 50 meg LSP from an RSVP perspective from router A to router D and pump 100 meg of traffic through it. Well, I understand what you're saying. Well, then what's the point of doing all this? See, I just dug myself a hole, didn't I? Well, the point is you can have certain destinations go one way through your network, because routing is still being based at some point in your network, at least on the ingress, right, of the LSP, on the IP destination field, right? So you could have half your destinations go via the northern LSP and half your destinations go via the southern, and you've sort of indirectly uncongested paths through your network.
Right. One of the earlier digressions on secondary LSP paths and statements, with that in mind, that is the link already secondary to the bandwidth of 0. It really doesn't matter at all, and you don't have to worry about it committing one way or the other.
Yeah. And, this, again, it's not necessarily that it can't be done, I think. I think we're still early on in the stages of this. I think in time, you'll see this capability where you'll be able to police the LSP itself, guarantee the bandwidth on it. So the traffic going through it won't actually be able to go above what's reserved for the LSP. Today it's not available, at least it's not available in our implementation. Maybe Robert, does it? Okay, so it's available in iOS. In our implementation today, it's not yet available. Any other questions? So then you have to set up a car profile, right? It's not automatic, Robert? Yeah. So you'd have to set up your QoS profile to map to the LSP, I guess, or your car profile. So just setting up the LSP won't automatically police the LSP traffic. Yeah, not quite all of the bells and whistles of ATM yet, but give it some time. It's all actually solving some problems though that ATM didn't too, so there are some benefits to it. Yes, back in the back. No, the ingress and the egress routers have to be the same. At least today they do. I've heard talk about trying to protect the egress router of an LSP. I know it's not available in Junos, and I'm not sure exactly how you get that to work. But today, yeah, any of the secondary paths for your primary LSP will, begin and terminate on the same two nodes. Well, you wouldn't have to reserve bandwidth on the secondary because, again, it's just a protection mechanism. But you'd have to have physical. Now, those two connections over two separate routers are the same router. Two separate routers. So yeah, you'd have to have two LSP. Well, and the thing is, BGP, by default is only going to pick one best, next hop. You can probably engineer what you're trying to do. I'm not sure I understand it completely. I could only hear half of what you were saying, but you can build two separate LSPs, and if your BGP decision came down to the best, IGP route or route through your network, then you have these two LSPs potentially. You could play with the metrics of those LSPs, or they'll just load balance across the two. Okay, if all the other because it's at some point, when BGP picks its best route, it's a BGP decision, so it plays with the attributes of BGP, and if, local preference and MED and none of that kicks in, and you get down to, well, what's the best, quote-unquote, IGP path through my network, then these tunnels come into play. And, what's that? More than one? Yeah, the IGP is load balancing on that eBGP or iBGP. If your IGP cost is the same. So you're saying, well, no, I think maybe the audience. Yep. BGP load balance. Yep. Traditional one is the best one choice. There is possibility and it's a theory, and actually in practice, pick more than one is better. And those balance something between two exit points for them. Okay, and theoretically, you're like, okay. Yeah. Okay. I was talking more to our capabilities today and thinking about how BGP goes through the decision process. Like similar on eBGP, right? By default, you're going to pick one best path, but you have knobs. You can do BGP multipath or whatever you call it, and therefore load balance across them. I guess I was referring to the default behavior or traditional behavior of BGP, but theoretically, yeah. Without any new knobs, BGP will only load balance through your network if they're equal cost IGP paths, I guess is what I was saying. Yeah. And the LSPs are part of that quote-unquote IGP path through your network. So I don't know if that answered anything in your question, by the way. Well, okay, yeah, because I couldn't hear all of it, but anyhow. Any other questions? All right, I guess that's it, guys. Oh, one more? I don't know.
I didn't hear the question.
I didn't hear it all. Yeah, that's what I thought I heard. And then when nobody else laughed, I was like, maybe I didn't hear the right question.
I still didn't hear it.
To find a good place to eat. Actually, Jeff used to live here. Good steakhouse somewhere?
Talk to me offline.
All right, guys, well, thanks for showing up. Hopefully we didn't bore you too much.